So emerging from the idea of the length of vectors, we have certain results which I will write down for you, and they might be useful later. So we'll just recall, you have seen these earlier. For example, the Schwartz inequality, which simply states that if I take the norm of AB, the modulus of AB, then this must be less than the product of the length of each vector. Okay. Similarly, there is something called the triangle inequality, which again states if I have two vectors and I take the resultant vector, then what about the magnitude of that? So if I take the length of this A plus B, then this is certainly going to be less than the length of A plus the length of B. And then of course we have the parallelogram inequality, which talks about A plus B square plus A minus B square, and this is actually going to be equal to twice of A square plus B square. So these are some results that we might use later on. I just thought we'll review them. Okay, so we have talked about this earlier, but let me formally write it down. So the n-dimensional Euclidean space. So we have Rn, which is essentially the vectors which are n tuples, such as A is A1, A2 and An. Similarly, I would write down B, which is these components B1, B2, Bn. And we are going to talk about their inner product AB, which of course is given as A transpose times B, and we have already seen this is A1 B1 plus A2 B2 all the way to An Bn. The Euclidean norm of A is denoted as, we have already seen this, and that would be square root of the inner product of the vector with itself, and that of course is going to be given as A1 square plus A2 square plus A3 square all the way to An square. Okay. So you already know this, but we have generalized it to an n-dimensional vector. Okay. Geometrically, we can visualize vectors which are two-dimensional, maybe in this plane, or three-dimensional, which could be in a room that you are sitting in. But we could also have vectors which are in n dimension, and these definitions, they essentially carry on in a very straightforward manner. How about functions? Can we use these ideas and generalize them to functions? So let me introduce to you inner product for functions. So the idea is whatever you know from vectors, most of it we can actually extend to functions, and it is most useful as we will see shortly. So let us talk about these functions fx, gx, etc., which are a set of all real valued functions. Okay. So we are not talking about complex functions at the moment. I mean, we could, but we don't really need them for the purpose of this course. And let's say we are going to talk about on an interval x, which lies between alpha and beta. The 2 points are included. So it's inclusive of the boundary. And they form a real vector space. So we are going to define f comma g as the inner product in the following manner. So we'll say fg is given as integral from alpha to beta f of x times g of x dx. So please note, this is a definition. There are other possible definitions. So several people would use the inner product with respect to a weight function. So they would say that I will take the functions fg, but then the product is a weighted product. So I will choose another weight w, which is also a function of x, and define this product with respect to a w. Okay, and that also is an acceptable value of the inner product. For the purpose of this course, we will stay with this definition of inner product. Okay, as you can see, this definition is linear, so it kind of satisfies the linearity property that I already talked about. It is certainly symmetric, okay, and it also has some ideas of positive definiteness. So you can check those, all the 3 properties that I wrote down a little bit earlier, they are actually satisfied by the way we have defined this inner product. And now I can even talk about the length of a function. Okay, so you will be surprised, just like you talk about the length of a vector, I would like to estimate what is the length of a function or what is the size of the function. So let's do that. So f is going to be simply the square root of f comma f, and this, as you can see, is going to be square root of integral alpha to beta f square, or maybe I should write fx whole square dx. So I can have these different functions f, g, h, which belong to a certain vector space, and each one of them I can assign a length. Okay, and just like I did earlier, I could even form the unit functions. So I could divide f of x with its length, and then they become normalized functions. Okay, so they have then length 1. So I could normalize g with its own length, h, there is another function with its own length, and so on and so forth, just like I do with vectors. Okay. We have a specific name for this kind of a measure. So f, as I said, is some kind of a length. So we define what are called as square integrable functions. Square integrable functions. These are those functions for which f is finite. That means integral does not blow up. So if I give you a function f for which this integral, the square of the function and the integral of that has a finite value, we have a specific name for that, we will call it a square integrable function. And we denote it by saying that f is L2. So it is square integrable. Okay, and this we will realize later has lot of value. So functions which are square integrable will have certain properties which we will use as we move on. Alright, let us look at another concept which is completeness. In fact, we have talked a little bit about it. So let us consider S is a set of functions defined on the interval x lying between alpha and beta. Let us say y0, y1 all the way be orthonormal functions belonging to S. I hope you are able to understand what is orthonormal. So we have already defined functions that have a length of 1 will be called the normalized functions, and functions which are orthogonal to each other, that means their inner products in pairs are 0. So what is being claimed is that y0 is orthogonal to y1. So the inner product of y0 and y1 is 0. Similarly, y1 and y2 are orthogonal to each other, and so on. So the set of such functions would be known as orthonormal functions. So this set is complete if every function f that belongs to the set S can be approximated arbitrarily closely, let us say up to an epsilon that I can choose, and of course epsilon is greater than 0. Okay. So that is the error in the approximation, which means in fact I could even get a exact representation by a linear combination of the functions. So what that means is that if I took f minus a linear combination of these orthonormal functions, so I choose a constant, let us say k0 and y0 plus k1 is another constant y1 plus k2 y2 and so on up to kk yk, and this should be less than epsilon. Okay, I think I should change this index because this may confuse you. So let me call this as m. Okay, I don't want you to get confused between the subscript and the constant itself. So what we are saying is f is a function that is given to you and it belongs to this set S, and I would like to approximate that by using these members y0, y1, y2 and so on, and at present I am using just m of them, and m is something that I decide. I can use 10 of these functions, I can use hundreds of these functions and so on. And the approximation can get as close as possible up to my specification. Okay? So it's a very tight approximation. If that happens, then I would call these functions to be complete. So let me give you an example. So if I had a function f of x defined on, let's say, minus pi to plus pi, then the Fourier functions which are 1 sine of x, cosine of x, sine of 2x, cosine of 2x, sine of 3x, cosine of 3x, and so on, they form a complete set. So if I choose any function between minus pi and pi, okay, that you give me, I can actually represent it in a Fourier series, and I can find out the linear combination. So a0, and then this is a1 sin x, b1 cosine x, a2 sin 2x, b2 cosine 2x, and I can determine these constants, and I can use as many terms as possible from this series and get as nice an approximation as you ask me to. So if you want a coarse approximation, I can probably just take the first 4 or 5 terms. But if you want a very good approximation, then I may have to take hundreds of these terms. If you want an even better approximation, perhaps I would have to take thousands of these terms and so on. Okay, and we have all looked at Fourier series in the past, and I hope you are able to understand what completeness means here. Let me give you another example which would be perhaps more relevant for this course. So example 2. So if I want to use, let's say, these bases, suppose I choose these as my basis functions. Okay, the monomials 1x, x square, x cube, so there are 4 of them. These form a complete set to represent any arbitrary cubic polynomial. Okay, so if you give me any polynomial, any general cubic polynomial, I should be able to represent it in terms of this basis, and therefore they form a complete set. As we argued earlier, is this unique? The answer is no. Okay, so I'll put a note here. So I could say 5, 3 plus x, 9 plus 2x plus 6x square, 5x plus 20x cube also form a complete set. Of course, these elements may not be orthonormal. We have not checked that. Okay, the definition that I gave you here kind of assumes that we are dealing with orthonormal functions. Okay, that's usually for convenience, but it is not mandatory for a complete set to have orthonormal functions. Okay. So you can see that if I took this as a basis, okay, so 3 plus x is linearly independent of 5. Similarly, if I took this element, I cannot get this by linear combination of the first two terms. In fact, any of these vectors, any of these functions, I cannot get as a linear combination of the other three. You can check that. If I try to get this guy, the cubic term, as a linear combination of the other three, you will see I will not be able to succeed because I don't have a representation for the cubic term. All right. What if I want to include a term like x to the fourth? Then I will be able to represent up to quartic polynomials and so on and so forth. I'll also like to give you an example of an incomplete set. So, example of an incomplete set. Suppose I use 1x x square, or maybe I simply use x cube to represent cubic polynomials. This will not work because I don't have a way to represent my quadratic terms. So if you give me a general cubic polynomial, okay, suppose you give me a polynomial which is written here, 5x plus 20x cube, I can certainly represent that. But if you give me this one, there is no way I can represent it with as little error as you demand by using these three. Okay? In fact, I would not be able to represent this term exactly, okay, because there is no x square term. So I hope you get a flavor of what is a complete set and what is an incomplete set. Okay. There is a result which is extremely important and we will use it. So let me state it for you. So let y0, y1, y2, etc. be a complete orthonormal set on the interval x lying between alpha and beta for the set of functions S. So this part is exactly what was stated earlier, nothing new here. Now is the operating part. So if I take a function f which belongs to this set S and is a continuous function, if this continuous function is orthogonal to each ym, then f is identically 0. So let me explain this a bit. So we have a set of functions which form the basis. I have called them as y0, y1, y2. And here's another function f. And the claim is if these form a complete set, so they form a complete set. And if f is orthogonal to each one of them, then it should be 0. Let's consider an example. So again the example would be a two-dimensional plane, x and y axis. So there is a unit normal here and there is a unit normal here. I take a function or a vector. So suppose this is an arbitrary vector, vector A, and the claim is A is orthogonal to the unit vector I, it is also orthogonal to a unit vector y, and both these form a complete set. Of course they do. For a two-dimensional plane, I and j form a complete set. So if A has no projection along x, it has no projection along y, obviously it must be a zero vector. I can extend this to 3 dimensions, and likewise I can also extend it to a function. So what we are saying is that if there is a function f and all the Fourier coefficients are 0, okay, so it is kind of orthogonal to each element of the Fourier series, then that function must be 0. Okay, this is a very important result and we will use this in the next few lectures. Okay, we will stop here today and we will look at a few more concepts in the next session. Thank you very much.